Pulleys 1. This video covers how to break down a pulley problem that covers both forces and suvat. So before dealing with the example written below, I'm just going to go over the general set of steps for dealing with a pulley problem. The first step, step 1, is to draw out the situation. Step 2 is to label all of the forces acting on the weights. These are typically tension and weight. Only in more complicated problems will other forces matter. Step 3 is label the acceleration with the double-headed arrow. And step 4 is apply F equals ma to each object, that's each mass, and produce the equation of motion. Okay, we'll apply these steps to example 1. So you can see here example 1, a vertical pulley system is constructed in the following fashion. A light inextensible string passes over a smooth fixed pulley. To one end of the string a 3 kg mass is attached and to the other a 5 kg mass. The system is released from rest. Even before being asked the question, it's sensible to draw out the situation, label all of the forces acting on the weights, label the acceleration with the double-headed arrow, and then apply F equals ma to each object. So part A, there's the pulley. On one side we have the 3 kg mass, and on the other side we have the 5 kg mass. That would be step 1, just drawing the picture. Step 2 would be to label all of the forces acting on the weights, so on each weight. So each weight must have weight acting on it, so this one has 3G acting, and this one has 5G acting on it. Both of these are connected to the string, so they both have tension acting on them. As there is only one string and the pulley is smooth, the tension is the same at both ends of the string. That's step 2. Then we should put on the acceleration arrows. The directions here don't matter too much. I'll talk about that more in a later video, but if you can get them right, there's just less, from the start, there's less confusion with signs. It seems fairly clear that the heavier mass, 5G weight, will fall down and the 3G weight will accelerate up. So those are the first 3 steps. The fourth step is to apply F equals ma to each object. So let's look at the 3G mass. We'll take up to be positive. Typically we'll use the direction of the acceleration as the positive direction. Then this will be, so tension acts up, weight acts down, that's why we're subtracting, and then it accelerates up with acceleration A, so 3A. And then if we apply the same thinking to the other object here, the 5G weight, we'll take down to be positive here because it's accelerating down, and so we'd have 5G minus t. Minus t here because t is acting up in opposition to down, our positive direction, equals 5a, the mass, times acceleration. Then let's look specifically at question A, calculate the acceleration of the system and the tension in the string. So that's essentially, we're just being asked to solve these two equations simultaneously. The easiest way to do this is by elimination, just adding the two equations together, and we'll end up with 2g is equal to 8a, which means that g over 4 is equal to a. Therefore a must be 2.45 meters per second squared. As with any simultaneous equations, as we have one of the variables, we can easily find the other. So we'll take the top equation, this one, and t is equal to 3a plus 3g. So t is equal to 3 times 2.45 plus 3 times 9.8. T is 36.75. Okay. And then in part B, calculate the speed of the 3 kilogram mass after 1.2 seconds. So any question that's mentioning time and speed, as if speed can change, is almost certainly a SUVAT problem. So before thinking too much about the question, it's worth just getting organized. So now we're dealing with 1.2 seconds. The final speed is what we're interested in. The system is released from rest, as stated there. The acceleration is the acceleration we worked out in part A, 2.45 meters per second. And for the 3g mass, all of this is taking place with up as positive. So we're looking for the equation that doesn't have s in it. So we'll use v equals u plus at. So 2.45 multiplied by 1.2, because u is 0. That's 2.94 meters per second. There's the answer. Okay.